Now let's switch gears and look at regression matrix. Very first one is explained variance score, and the value of 1 is a good score, lower values are not good, and it's given by this relation shown here, which is 1 minus variance of difference between the y true and y pred divided by variance of y true. And this is the implementation. We have these are identical values, so we have a higher value of the score 1. If there is a mismatch, the value drops and can go down in negative range, and if the values somewhat agree, then we have value closer to 1. Now let's look at another metric, which is max error. So this is simply maximum difference between the y true and y pred as shown here. And the implementation here we can see max underscore error, and then in parentheses we have y underscore true comma y underscore pred. Here both the y true and predicted values are identical, so we have an error of 0. If there is a mismatch, then we get a value that is not 0. And in this case we have the difference between -3 and 3 is the largest, so that's the output we have. Now in case of mean absolute error, we are simply taking the difference between y true and y pred, dividing it by the number of samples, so sum of these difference and divided by number of samples. Again, the score closer to 0 is good, and here we can see the mean underscore absolute underscore error. For this first case, we have value of 0. The second place, we have value of 3.25. Along the same lines, now we have a mean squared error. So the difference is that here we are not only taking the difference, but we are squaring the value of difference and then adding it, then dividing by the number of samples. So that's the mean squared error. A point to note here is that if you need to pay attention if the algorithm returns a negative value for mean squared error, in that case the interpretation would change. So here in this example we have positive values returned, so the lower the value the better it is. um, if negative values are returned, then you need to switch that concept. So as we spoke earlier in this set of videos, uh, negative 1 would be in that case a higher value as compared to negative 10, and so that would negative 1 would be a better value if negative values are returned. If positive values are returned, then 1 would be smaller than 10, so 1 would be a better value. So here we have 0, which is the best value, and those are identical for y true and y pred. And as the differences change, we get values that are higher than 0. And this is generally used to compare different models to see which model gives a lower MSE. Next, we have something called as negative root mean squared error. And for this, we can use the same function we have, except that in this case, where we specify squared, so there we can specify um, that there should not be any squaring. So we can set it to argument can be set to false, and so then we get the values that are shown here. Along same lines, we have something called as mean squared log error, and therefore we have it is given by this relation, where instead of simply taking the difference between y and y true and y pred, what we are trying to do is taking log value. So we are adding 1 and taking a difference of the logarithmic values, and this helps if the differences between the true and predicted values are very small. So this can may help identify those differences. Here is the implementation of mean squared log error. In the very first case, we can see that only positive values are used, and that is a requirement. The values are identical, so we get a score of 0. And if there is a mismatch between the values, we get a value that is non-zero value, as we can. Next, we have negative median absolute error. And this negation if need to watch, if you are doing cross validation, you may be getting an output with negated values, so you need to pay attention to that. The mean absolute error is given, median absolute error is given by this value, which is median of the differences between the y true and y pred. And here we have the values again, median underscore absolute underscore error, y between these two. And if the differences are identical, the best score of 0. If there are differences between the true and predicted values, then we get values that starts to move away from 0. Then we have R2 square, which is coefficient of determination. So if you remember correlation coefficient R, the square of that would be R square, and that's the coefficient of determination. But then in this case, you need to pay attention that the R square value may be negative, as it is mentioned in the docs, because it may not actually be a square quantity of the R. So that's what I've written here, and this is given by the relation shown down here, which is 1 minus fraction of, this is y minus y pred, and then y minus y bar, which is given, which is the mean shown here down below. And in this case, a value closer to 1 is the best value. And as we can see in this very first example, R2 underscore score, y true, y pred, these two are identical, we get a perfect score of 1. If the values start to differ, then we get a value, a negative that I spoke earlier, or values that are lower than close to 1, 0.9 as here. There is another set of scores which are based on this Tweedy deviance, and as shown by this relation down here, we are looking at gamma mean, gamma deviance, which is given by this relation, and where the Tweedy the power parameter is set to 2, and these are the values for that. So in this case, a value of 0 indicates best score, values away from 0 indicate a not so good score. Now let's look at mean Poisson deviance, and in this case the value of p is set to 1, and this is the equation that is used to calculate the score. Again, the implementation is the same. We have the mean underscore Poisson underscore deviance, y2 y pred, and if the values are do match, then the values 0 or closer to 0. If the values are farther apart between true and pred, then the score starts to increase. And then we have mean absolute percentage error. Again, this can be returned as a negative value, and it is given by this relation here, where we are taking the absolute difference between the true and predicted and then dividing it by this term, which is and therefore which is epsilon and modulus of on the true value, and thus the percentages are within the range 0 and 1 divided by epsilon. And here we have the mean underscore absolute underscore percentage underscore error in parentheses y true and y pred. Values are here, the values are identical, so we have value score of 0. The value starts to differ, we get a score that increases. And then we have a D2 score, which is coefficient of determination, and this computes the percentage of deviance explained. It is given by this relation. We won't go into the details beyond this, but we'll look at the implementation where we have this value. So if the score is closer to 1, then we have a perfect score. So 1 is best, and 1 is best, and then if the values move farther apart, then we get a score that's below 1, as we can see here. And then we have pinball loss, and this is used in quantile regression models. So what we are doing here is taking the maximum value between the y and y true or 0, whichever is greater, and then we have this term alpha in here. So we take a sum of those and then divide it by total number of samples. Here, let's look at the implementation. We have the mean underscore pinball underscore loss, and the lower the value of loss, the better it is. So here we have identical values between true and pred, and so we have loss of 0. Now, if the values are different, then depending on upon what value of alpha is chosen, we get different values for the output score. Again, a point to note here is that we are using the mean pinball loss, and so lower value, the better it is. Now, we have completed clustering, classification, and regression. Now let's look at dummy estimators. So why these are used? So in scikit-learn provides these to so that you can use it to get a kind of a baseline on the classifier or regressor. So what is the baseline that you can improve upon? So for classifier, these are the options available: stratified, most frequent, prior, uniform, and constant. So stratified classifier, dummy classifier makes random predictions. Most frequent one predicts the most frequent label. Prior maximizes the class prior, and the uniform generates predictions uniformly, and constant predicts a constant level that's you can specify. And similarly for regressor, there are mean, median, quantile, and constant that can be predicted as a baseline. The implementation of these is very straightforward. So you have CLF is equal to dummy classifier, you can specify the strategy, and you can fit it on the train set, predict on the test, or score on the test. And same thing for the dummy regressor, you can specify the strategy and predict on the fit on the train and predict on the test set. And the possibilities for strategy are listed here: median, mean, median, quantile, constant, and then here we have stratified, most frequent, prior, uniform, and constant. So that was it for these series of videos on metrics and scoring. I hope by by the understanding different types of options available with scikit-learn, you'll now be in a better position to evaluate and quantify how well your model is doing, be it clustering, classification, or regression. And you could now also try to incorporate the dummy classifier, dummy estimator. It could be classifier or regressor in your models to see how your actual model performs above the baseline that is predicted by these dummy estimators. If you have any comments or suggestions or any additional questions, please feel free to post them in the comment section below. I hope to see you all in the next video. Until then, please like, share, and subscribe. I really appreciate your support. Thank you so much.